All right, I guess we'll get started. Welcome on this very chilly morning. All right, so a few announcements. So your week 3 test is going to be due tomorrow at 9 p.m. Lots of people still haven't done it. Do it. Yeah, better to do it and sort of bomb out than to not do it and then not know where you're at, okay? So make sure you give it a go. The week 4 test will be coming out tomorrow. Basically, as soon as the end of the test 3 comes out, then test 4 comes out. So lots of fun times ahead. Tomorrow, June 25th, is the census date, okay? Last chance to drop out without financial penalty. Of course, I don't want to encourage any of you to drop out. I'm just letting you know that that's the case. And the first assignment is due next week on Friday at 6 p.m. So if you need help, make sure that you book a help session with someone. And yeah, get onto it because those are being booked out quickly as well. All right, so just a reminder on plagiarism. Get help from the right places. So, your tutors, your lab instructors, me, lots of people there that can help you with stuff. The forum is really good to put some questions in. Don't ask ChatGPT for you, doing your code for you. We do run plagiarism checking on all the submissions. It works pretty well, and it would be kind of a sad way to lose your. I don't even know what happens anymore, but I'm sure it's very bad. So just don't do it, and then we don't have to worry about what happens because it's an unpleasant situation. All right, so today we'll recap on integers, and we'll do a few exercises with that. We'll look at instructions in MIPS and loading things in MIPS and how it deals with signed and unsigned numbers. And then we'll start looking at bitwise operations. All right, so this number here, what does it represent? Now, instantly, your brain's probably going to some sort of binary number. But without knowing what the type is, we can't really say. So it could be an integer, it could be an unsigned integer, it could be a float, it could be a Unicode character, it could be an instruction. Okay, so we need to know what type we're looking at to determine what a train of zeros and ones might represent. So don't get tripped up with that. Brain instantly goes to probably some sort of unsigned binary number, but may not be the case unless you've been told what it is. All right, so let's recap. So unsigned integers are those that run from 0 through to 2 to the power of 32 minus 1. So that's all of our kind of bit slots from the 0th through to the 31st, all with ones would be our biggest number, and our smallest number would be 0. Okay, so all ones, maximum value, all zeros, minimum value. All right, so signed numbers. We sort of looked at this last week. It's obviously not made for human brains, it's made for computer brains. But two's complement, which is what we use for signed numbers, works really well because it allows us to do arithmetic in the normal way without having to make any great changes or create any crazy control logic around it. So the way to do it is to take sort of the maximum, so 2 to the power of 8, subtract the number that you want to have a negative representation of, and that will give you your representation. And if you wanted to go from a binary number through to a negative number, then you would take the representation of that number and subtract the big number, and then you get -5. Now, I always do it, let's see if this works. I told you I would find a solution, so hopefully this is a solution. But, you know, I usually do it like if I need -5, then what I would do is I would write the binary representation of -5, of 5. Then you flip all the numbers, so it's a 1, 1, 1, 1, 1, 0, 1, 0, and then you add 1, and that's how you get 1, 1, 1, 1, 1, 0, 1, 1, which is what this number. So it's an easier way to do sort of on a piece of paper and pencil, and it also means that you can do a bit of a sanity check. I've never actually done it this way, like in the wild. I've always done it by flipping all the bits and adding 1. But up to you what works, what you remember, I guess. This sort of method here, where you sort of flip everything and add 1, is easy to remember and quick to do. So that would be my suggestion to you. So that's 2's complement, and that allows us to sort of run from -127, this is for an 8-bit number, all the way, I've done it backwards, from 127 all the way through to -120, it would be 128. So, and everything in between, and there's only 1 0, so it's a nice representation because we can just add and subtract and do all that without any issues. So yes, so these run from the number of bits to -1, so negative, all the way through to positive, that number. So the biggest number has a 0 at the front and then all 1s, and the smallest number has a 1 and then all 0s. Okay, and those are and as we have more bits, you know, so if we go to 64 bits or 128 bits, we can represent bigger and bigger numbers. Okay, so hopefully from that you can see that depending on whether a number is signed or unsigned, it will change what that what it represents. So this number here, we can see that it's got a 0 out the front. So its unsigned and its signed representation will be the same. So if we wanted to represent that number, we would just find the bit positions. So these are 8 bits. So we've got 2 to the power of 6 plus 2 to the power of 1 plus 2 to the power of 0. I have no idea off the top of my head what that number is. Is it like 66? No, 67. Is it 67? That's monstrous. Okay, so I think that's what it is. So this number here, if it's an unsigned number, then you do the same thing. So it'll be 2 to the power of 7 plus 2 to the power of 6 plus 2 to the power of 1 plus 2 to the power of 0, and whatever that is. But if it's a signed number, then we have to sort of treat this a little bit differently. So if we If we have that number there, we know that it's signed because it starts with a 1. So then we do the 2's complement thing, so we can work out, so that's negative, and then we add 1 to this, so we're going to have, I've done this very messily, let me just, how do I erase? Yeah, that's erase. Not erasing. Okay. Right, let me do it over here. All right, so we flip all the numbers. Okay, then we add 1. Like that. So it's minus whatever this number is, which will be minus 2 to the 5 plus 2 to the 4 plus 2 to the 3 plus 2 to the 2 plus 2 to the 0. Okay? And that will give you a number. And obviously, this number is different depending on if it's unsigned or signed. So it is monstrously 6.7, and the other one adds up to 195. So no, again, we just add up where there's a 1, so 2 to the power of 7, that's bit 7, bit 6, bit 1, and bit 2. And then for our signed, because this number starts with a 0, it's just going to be the same, so we don't need to do anything special. And the other one, it's used the method of working out what this number is, minusing 2 to the power of 8, and then you get 61. Okay, and the way that I would have done back here hopefully gets you to the same place. Does that all make sense? Probably worth doing some practices yourself, making sure that you can do it. It's straightforward once you get into the zone, but the important thing for you as programmers is to just take notice of when you've got signed numbers and unsigned numbers. That's the bit where you could get into trouble. All right, so we also looked at the concept of Endianness. Okay, so there's big endian and little endian. So big endian stores the most significant bits first in the low address, and then the least significant in the higher addresses. And little endian stores things in the little bits first, and then in the higher address it puts the most significant bits. Now it's not really a big deal either way, but it is a big deal to know which Endianness you're dealing with in a particular computer system. Different designers have made different choices for different reasons, and especially if you kind of get into embedded systems and that sort of thing, you will find people have made different decisions about Endianness. It is a bit sad that there's not really a standard for this stuff, but nobody thought there should be, so instead, for the last 30, 40 years, people have been teaching Endianness because no one can agree. So if we remember from last time, let me see if I can bring up my browser. Okay. All right, so MIPS. All right, so if we have a word here And well, firstly, if we just look at how it's saved, right, we can see that it's storing the smaller stuff first. So that tells us that MIPS is little endian, okay? It's weird. This is off the screen. What just happened there? Okay. Sorry, it's like crazy land on my computer here. All right, so yeah. So MIPS web is little endian. So that has implications if you want to access particular bytes or half words. Okay, you need to know which address you want to point to in order to pick up the correct bytes or half words. So when we're dealing with half words and bytes, we also have to think about whether things are signed or unsigned. So for there's two different instructions in your MIPS instruction set. There's load H and load B, and those are signed. So they're going to take whatever you're loading and make them a signed number. If you want it to be unsigned, you have this LHU and LBU, and then it'll treat whatever you're loading as a byte or half word as an unsigned number. And it really does depend on what you want to do with that. We don't need two versions for loading a word because the word is taking up the full 4 bytes of memory space. And so its most significant bits will be the indicator as to whether it's signed or unsigned. And that's how you deal with that. So if we had a byte that stored, don't forget our hexadecimal system. So just by way of just remembering, so hexadecimal numbers, each number represents 4 bits. So 8 in binary is that, and 0 in binary is that. So you can quickly change between hexadecimal and binary just by looking at it. So this number here starts with a 1 and then has all zeros. The question is, what would we store in these other registers when we're wanting to load or store this particular byte? Okay, so if we set these other registers to 0, then it means that we're treating it as an unsigned value, and we're just taking this byte as it is, unsigned. If we want to consider it as a signed value, we put 1s into all these other registers so that we're extending out the sign bit. So we're saying this is a sign bit, and then we extend it throughout all the registers. So we've saved a signed word as opposed to an unsigned word, which then just treats this as this particular 8-bit binary number without any sign. So the first bit is not indicative of the sign of the number. All right, so let's look at MIPS. So in this piece of code, I've loaded the byte T1. I'm going to sneeze. Okay, I'm not going to sneeze. I think the original word was 1, 2, 3, 4, 5, 6, 7, 8. 5, 6, 7, 8. Okay, so if we have a look at our register values here, okay, we can see that when we load the most significant bits, it gives us 128. That is because this, I think it was a byte that I was loading. Yeah, loading a byte. That is because the last two, the 7, 8, it doesn't start with a 1, so it's treated as an unsigned number. If we were to change my word into something that had ones in the front, all right, then it treats this as a signed number, because EF is, I think it's 1, 1, 1, 0, 1, 1, 1, 1, 1. So that starts with a 1, so it's filled, because we're doing a load byte, it's filled all the other registers with a 1, it's extended the sign bit, so it thinks it's a negative number, and so it gives you a negative number. Now, if you didn't want to treat it as a negative number, you would put the unsigned, okay, and then it just treats it as a positive number, okay? So that's why you would use signed or unsigned. Signed just takes the first bit that's in the register, which in this case, a 7 is 0, 1, 1, 1. So the first bit is a 0, so it says, oh, I'm unsigned. So it just loads it as a positive number. But when we put C in, C is, what is C? It's 1. So wait, I have to go through this in my, so that's A, B, yeah, so C is 1, 1, 0, 0, and that starts with a 1, so it extends the 1 out as a sign bit, and it loads it as a negative number. Does that make sense? Also worth playing around with this stuff, just, you know, loading different values. It doesn't help that you're constantly having to switch your brain between hexadecimal values, and this is also in here is the base 10 value as well, just to mess with your mind a little bit more. So yeah, worthwhile just going through, making sure that makes sense. The short of it is, if you're LB or LH, it's going to give you a signed number. If you put the U after it, it'll give you an unsigned number. And that's important depending on what you want to do with that byte or half word when you load it. Okay, so we went through this example. Well, we didn't, but half words are kind of, it's kind of the same thing. You're loading this in. It extends out with zeros because it's the 5 is given by 0. I've got a pen. 0, 1, 0, 1. Okay. So then it extends this as the sign bit and into zeros. Okay. All right. So, yeah. Any questions, issues, complaints? All right. So you might have noticed that we can have this decompiled version here that gives us, you know, a lot of numbers. And what do these numbers mean? And you know, what does it represent? We saw in our MIPS instruction set that an instruction is, oh, that's the memory bit. Where does it talk about instructions? All right, there's a picture coming up anyway. So if we pull this out to be a binary, so these are hex, so that's 0 and that's 1 and so on, we can see that we get this weird number, and this weird number actually is what MIPS uses to tell it what to do. So it's just binary words saying things that make sense to the hardware that then do operations based on what this bit sequence is. So yeah, this is the thing I was looking for. So our MIPS instructions basically have a code that's at the beginning and end in some cases, then specifies the registers that we're using. Sometimes when we do, say, a immediate, we're actually loading a constant value or address. And this code sequence all kind of relates to these different numbers. So this means add immediate. This is the code for register T0. This is the code for register T1. And this is the binary word for 12. Okay? And so this sequence of ones and zeros is actually what the processor uses to work out what it has to do. It's everything that you write in MIPS is actually just a code in ones and zeros that then turns control logic on and off, does particular operations in the arithmetic logic unit. And so the reason, obviously, shouldn't have to be said, that we kind of translate this into some kind of readable thing is because it'd get pretty hard to understand what this means. And I'm sure there's like people that are like super deep into it that can look at a code like that and go, oh, that means add immediate this. But most of us mortals are just going to use the regular instructions and map them to, and let the computer map it to these particular codes. All right, so let's have a look at what this means. So we have an opcode that kind of has all zeros and then a 1 and zeros. So if we come over here, these are all the different things that we could be doing. Right? These have got all zeros, but different back here. All zeros, different code there. So we'll see if we can find where it is. All right, so this has the zeros and then the ones. Okay, so it looks like that command is an add command. Right, so that's add. All right, now we have to find this. I think that this is this way around. Yeah, this register here. So this is where we want to store. This is the register, the RS register, right, where we want to store the value of our operation. So this is just, we work out what the binary is. So it's 2 to the power of 4 plus 1. So that's going to be, I can press the button. That's going to be 17, register number 17. And then this one here, this is just a 9. So this is register 9. And this one here is register 8. Okay, so these are just all zeros. So that means it's not anything. And this coupled with this was our instruction, what we're doing. So then these aren't how you've been writing registers. But if you look at your MIPS, actually you can see here that the registers actually are called numbers, and we've just kind of aliased them with some letters that make sense. So 8 and 9 are T0 and T1, and 17 is S1. Okay, so we can further simplify this whole code, and we get S1. Okay, so if we add this into MIPS. Right, so we add an instruction. Okay, so we want to store in register S1 T0 plus T1. Okay. It's T1, T0. Okay. All right. And there is our instruction. Okay. Magical, really, truly magical. And that's essentially all of these are just deconstructed the same way. It's just basically a decoding exercise that happens every time you write your C, it gets compiled into a machine language, and the machine language is all ones and zeros and things that look like, that tell the processor, load this, add this, store it here. It's pretty simple, basic instructions that altogether do quite complex things. All right. So now we'll look at bitwise operators. So we've kind of seen that, integers are everywhere. Next week we'll look at floating point numbers. But we do a lot of things with integers. And where possible, we try to use integers as much as possible because floating point adds a lot of complexity. And the accuracy of floating point is very dependent on how much room you have to store those really big floating point numbers. So integers are very useful. If you're into embedded design, that sort of thing, then most of your life is spent with integers. And so bitwise operators helps us use our integers for control and for security. So particularly cryptography and embedded systems use lots of bitwise operators. Of course, there's all these other things that use it as well. Certainly data compression is a big one. So being able to use bits to do things is quite useful. I didn't realize how small this was on the big screen. Oh, this is weird. All right, so what operators exist? So all the CPUs have bitwise operators. So you have sort of an arithmetic logic unit. The arithmetic is your adding, subtraction, multiplication, division. Your logic operators are where you're doing all your bitwise stuff. So this is your AND, your OR, your exclusive OR, your NOT, and then shifting left and right. So these are your sort of basic bitwise operator. So there's bitwise ANDs, and then there's logical ANDs, and these things are treated differently in the system. If any of you have done discrete mathematics, you would have had a lot of fun learning about this stuff. Also, keep in mind that in your journeys through academia, you will maybe do a course in electrical and they'll use different symbols for these things. Or you'll do a course in mathematics and they'll use different symbols again. I don't know why people do this to our poor little brains. They should just decide on something and use it, but this is not how it works. For us, we use the symbols that are here. These are the symbols that mean these things for this course, and they're what the C languages uses as well. But just beware, different languages will use different things, different subjects, different parts of the university will use different symbols. And it is easy to make a mistake because you might have been spending your whole time thinking that tilde was not, like a bitwise not was a exclamation mark, and then you get here, and it's a tilde, and it's very unpleasant, I think. But yeah, it's just to say that make sure you know it for this course, and you might have to wipe your brain afterwards and do something else. All right, so logical AND, you've probably seen this quite a bit already in C programs. We use it a lot when we're doing some sort of conditional operation, so an if this and this, or while this and this, and that's a double ampersand, okay? That's our logical AND. It's just looking for both parts of our Boolean equation to be true. The single ampersand works on each bit, okay? So it's not looking at the whole and going, this is true. It's looking at each bit in compared to another bit sequence. So, if we had a bit sequence of this and a bit sequence of this, like it would do its operations on each pair of bits rather than the whole thing. All right, so what is an AND? Have you guys done AND and that sort of thing before? Maybe, maybe not. That's okay, that's why we're here, to teach you these things. So the people that might have done the maths or the electrical engineers would know ANDs as sort of this kind of, like that's the circuit symbol for it. It's like a little thing like that, and you take two values and then you have an output value, and these are all in ones and zeros. So nice thing about bitwise operations, 1 zeros all over the place. So an example of AND, so this is a Carnot map for AND, right? And it basically tells you for different inputs what the outputs will be. So 0, 0, we get a 0 at the output, 1, 0, we get a 0 at the output, 1, 0, we get a 0 at the output, and only do we get a 1 when both of the inputs are 1. Okay? So, and both things have to be true. So you can see this sequence bits here. When we have two ones, we get a 1. When we have a 0 anywhere, we get a 0. Okay, so AND only is true when both inputs are true. Okay, and it makes sense sort of semantically. This and this, you're assuming that both things are true. Okay, so this sort of thing is useful for checking if a bit is 1 or not. Okay, and that might be useful because you've seen the MIPS code that tells you something to do. If you wanted to know what the code was, the control circuitry and that sort of thing will be using things like ANDing and that sort of thing to work out the value of particular bits so it knows what to do. All right, so for any value of x, x could be a 0, x could be a 1. If you AND it with 0, what do we think the output should be? Everyone's very shy. 0, right? So AND anything at all with a 0, and it's a 0. If we AND anything at all with a 1, what would the answer be? It'd be whatever anything is. So if anything's a 0, then it's a 0. If anything's a 1, it's a 1. Okay? All right, so this allows us to do interesting things, as I said before. So work out whether a particular bit was set. Okay? We use long sequences of 1s and 0s to do control and to give instructions all the time. So understanding which bits are on and off can help your greater system know what to do. So we call this a mask. So here we have a number, our x. It's this number here. Then we have a mask. So this is a good mask because it's got all 1s here in these positions. And so when we AND these two, we'll only get the result of what's in here that, yeah, so we'll pull that out and everything else will be a 0. Okay, so that's our mask. We put our mask onto our X, and it'll be this bit and this bit is a 1, this bit and this bit is 1, and this bit and this bit is a 0. So it'll pull out just those last few bits. And it seems extraordinarily, I guess, arbitrary to you, but sometimes you want to know, think about that big code of MIPS instructions. What you probably want to do is mask out everything except the register to find out what the register value is, or mask out everything to find out what the operator is. Okay, and that allows you to be able to know how to control the data within the system. Okay. Okay, so all right, so we've got this code. All right, so it shows you how you can check a particular bit using an AND, okay? So let's say we've got a number X, and we want to know the position at bit 1, what that mask would look like. Okay, so if we think about it, bit position 1, if we've got, well, we've written it here. So it's this position that we want to check at. So we want to put a 1 there and then 0 everywhere else. Okay, so what we want is 0, 0, 0, 0, 0, 0, then a 1, and then a 0. Now, what value is that as an integer? Okay, that's going to be 2. Okay. So all right, so live. Okay, so in position 1 in 6 is 1. Okay, so if we think about what 6 looks like, 6 is looks like that. So there's a 1 in that bit position. Okay, it's not particularly exciting doing it this way, but you know, it just shows you what you can do with bitwise operations. Okay, and you know, this could be a code to do something, and this bit means do an addition. Okay, and this bit might be, you know, what the number is or something. So being able to pull out parts of a big binary number, this is the way that we would do it. So how could we set the bit at position 2 to 0? Okay, so let's say we have this number, so number 5. So 5 is, I'm glad we're using little numbers here. I wouldn't do very well. So 5 is a 1, 0, 1. Okay. So what do we want to do? We want to set bit in position 2 to a 0. Okay. What would we do for that? Now we could, this sort of, if we want everything to remain the same, and we're doing an AND here, then we remember from before that ANDing a 1 with anything gives us a whatever our original value was. So if I ANDed this number here with 1, 1, 1, 1, 1, 1, oh no, bit position 2, 0, 1, 1, then every single value, so the output would be what was originally in the original number, except at bit position 2, because ANDing anything with a 0 gives us 0. So this is the value that we want to put in our mask. Does anyone want to tell me what that is in signed integer? Well, I guess it can be, this is an unsigned number actually. So what is the unsigned number of this? Because I just looked up here, we've declared it unsigned. So what is this as an unsigned number? If anyone's got a calculator, anything, anyone want to help out? I guess I could pull out my phone. Just yell it out if you get it. Does everyone know how to do it? Just don't have the tools to be able to work it out? Or like way too shy? Yes? 251. Okay. So now we're going to do a AND between the mask and Z. So we know that this is our Z, which is 5, and this is our mask. Right, and then we're going to print the result. Okay, so the result is 1, which makes sense because we've turned this into a 0, and so then we got all zeros and then a 1. So, yay, it worked. All right, does that make sense? It's kind of crazy doing it this way, I have to say. But, yeah, as long as the magic of mathematics works, I guess that's the main thing. All right, we'll have a few minutes break, stretch our legs, warm up a bit, and then we'll come back and finish it off. All right, we'll get back on with it. So yeah, okay, so we showed how we can use bit masks to either set a bit, right? So in the last example, we wanted to set a bit to 0. So we made a mask with 1s everywhere that we wanted to keep the original values, and we put a 0 where we wanted to set that particular bit. And we also looked at if you wanted to know, if you wanted to check a particular bit, how you could do that. Okay? So hopefully that all makes sense now. So another thing that you can use bitwise operations for is to check if a number's odd. Now obviously we've done this probably ad nauseum since you were 5. You just find the modulus when you divide by 2, and then you've got if it's odd or even. Can we have a bit of quiet here, please? Okay. So yeah, so there's an obvious way to do it. The unobvious way, I guess, is to think in binary. So if you look at this table of binary numbers, you'll see something of a pattern that emerges every time something is odd. Okay, so number 1, number 3, number 5, number 7, they all have a 1 in their least significant bit. So we can use this as a way to check if a number's odd. We can just check what the last bit is. If it's 1, it's an odd number. If it's 0, then it's an even number. All right, so a 1 in the last place means that it's a odd number. So one way to check this would just be to use a mask, right, that we had 0s everywhere and just a 1 there. And we do an AND. I'm not great at drawing ampersands. And between those two bits, if it's a 1, then it's an odd number. If it's a 0, then it's an even number. Okay? It's, it's, you know, the way to do it like this way, it's, you know, we're not saving any lines of code here. It's just an AND between whatever the number is and a 1. And, you know, I guess if the percentage sign was broken on your keyboard, this would be another way to do it. All right, so that's AND, okay? So AND is good for checking the value of bits, and it's good for setting things, particularly setting things to 0. It's not great at setting things to 1, okay? So if we want to set things to 0, AND is your operator. The other operator is an OR. So an OR in electrical engineering and computer science, in mathematics, it kind of has a symbol that looks like that. It's a little Carnot map. It's basically opposite land to AND. As long as there's a 1 in there somewhere, it'll give you a 1. Okay, so if there's a 1 and a 0, you get a 1. If there's a 1 and a 0, you get a 1. And if there's a 1 and a 1, you get a 1. So very, you know, 1 heavy. As long as there's a 1 there, it'll be happy. So if we look at two binary numbers, wherever there's a 1 in either of these numbers, we get a 1 out. Okay? All right, so very different from our friend AND. If we have X ORed with a 0, the output will be whatever X is, okay? So if X is a 0, the output is a 0. If X is a 1, the output is a 1. If you've got anything ORed with a 1, then you're always going to get a 1 at the output, okay? So in this next example, we had our mask. If we did an OR, then we're going to get ones where we have our mask. So essentially, our mask is a way of setting bits instead of checking bits. All right, so the other popular type of operation is called negation. I should mention also that in electrical engineering and in computer engineering, we call these symbols, we call them gates. So this is an OR gate. A negation is given by this cute guy here. So it's only got one input and one output. And in electrical engineering, computer engineering, we call it an inverter. So it takes whatever the input bit is and inverts it. Okay. Here we use the little tilde. You will probably see places that use values and put a line across it to mean invert it as well. So if you do any discrete maths course or anything like that, you'll learn De Morgan's laws and all of that, and you might see these kind of notations. It's all the same thing. In C, we use the tilde, and our little map here is just well, it's only got one input. So if your input is 0, then the output is 1, and if your input is 1, then the output is 0. So it just takes whatever you have and turns it into the land of opposites. This stuff is, the inverter is particularly important because all of the hardware that computers are built of, they use a particular kind of hardware called complementary hardware. And that hardware, everything is a negation. So it's easy to make NAND gates instead of AND gates and NOR gates instead of OR gates. And you know, our ones and zeros are important because inside, under the hood, you have these little transistors here. And you have different types of transistors. These are like switches. And this is what this gate looks like in computer land. And so if you have a 1 here, it turns this switch on to conduct, which pushes it down and makes it a 0. If you have a 0 here, it turns this gate on to pull it up to a high voltage, and so then you get a 1 at the output. That's essentially why we're using 1s and 0s everywhere, because it actually is really compatible with this hardware, and it allows us to do lots of things really, really quickly. So some of the technologies that these little switches are made in, it's like 2 nanometer technology, or even less than that people are looking at now. So you can imagine if you've got lots of little switches that just want 1s and 0s, they can turn on really, really fast and do lots and lots of computations. So even though that MIPS code looked extremely laborious, and even though it was a little laborious for us in C to do a mask or something, in the computer lands, you can lots of zeros, lots of ones, doing lots of things at very high speeds, 10 gigahertz, whatever, and performs a lot of computations very quickly. The language of 1s and 0s is just what it loves, so it's easy for it to do this sort of thing. So that's just what's under the hood. You don't need to know that for this course, but if you're ever wondering why we care so much about binaries and bit operations, this is mainly the main reason why. All right, so if we had a binary number and we put it, we did a negation, each bit would just be the opposite of what it was. So if you think back to 2's complement, you know, when I wanted to get -5, say, I basically am doing a negation for each one of these bits, okay, and then adding 1. Okay, so it's very much, you can imagine how this might look in like physically. You'd run the number through an inverter and then add a 1, and then that's it. You've created a 2's complement number. Yes, I think the thing to note here is that negation is not making it negative. Negation is just taking a bit and flipping it, okay? Whether a number is negative or not depends on how you have declared it. So if you've declared it as a unsigned or signed or that sort of thing. All right, so we can set and unset bits using our masks. So yeah, so if we have a mask of 7, so remember 7 is 0, 1, 1, 1, we can set the least significant 3 bits, okay, using an OR function. So any number ORed with a 7 will make the last 3 bits 1. Okay, so if we have, I'm just making this number up. So if that's our number and we want to set those last 3 bits, the easiest way to do it would be to OR it with this mask, which is our 7, right? When we OR it, we go this or this is a 1, this or this is a 1, this or this is a 1, and then it keeps the rest of the number as it was before. Okay, so that's the OR function with the mask has allowed us to set particular bits. If we negate that mask and use an ampersand, so an and, we can unset things. So we could go, our original thing was, so after we set things, we had this. Yep. So then if we want to unset those 3 bits, we could AND it with this number and do an AND. So anything with a 0 is a 0, and then AND anything with a 1, and it's whatever it was originally. Okay, so you can start to see how you can manipulate bit sequences. You can change their meanings just by using masks, ands, ors, depending on what you want to do. Okay, so this is the example of the negation of that bit mask. That gives us this, and then we do a AND operation. We get the original bit position holding, but the last 3 bits we've changed. Okay. All right. So another operator is exclusive OR. So exclusive OR looks like this. And exclusive OR, also the hat operator, you know, that's used for the C language, other languages, other, you know, things that you do will use different symbols. So our exclusive OR is a little bit different from our OR. So it's exclusivity means that essentially you think to yourself, you get a 1 when both bits are different, and you get a 0 when they're both the same. So if you've got 2 1s as the input, you get a 0. 2 zeros as the input, you get a 0. But if you've got a 0 and a 1, or a 1 and a 0, you get a 1. That's the exclusive OR. So it sort of allows you to do a comparison between 2 numbers. So if they're the same, you'll get a 0. If they're different, in the places they're different, you'll get a 1. Okay, so that can help for, you know, checking what bits don't match, used extensively for cryptography, also used in additions. So when you're making an adder in sort of hardware, each bit is added using an exclusive OR. Okay, and then you have an AND gate to get the carried bit. So yeah, very, very useful type of function. So if you have any number exclusive ORed with 0, it's going to be the number. Let me just get my brain around this. So All right, so if I've got 2 zeros as my input, I'm going to get a 0. If I've got a 0 and a 1, I'm going to get the 1, and 0 and a 1, I'm going to get the 1. Okay, and then if you've got a 1, you're going to negate. So if you've got a 1 with a 1, you're going to get a 0. Sorry, this should be a 0. If you've got a 1 and a oh yeah, if you've got a 1 and a 0, then you're going to get a 1. So yeah, flips the bit. All right, makes sense. So a little bit different from the other ones where you're either always going to have a 0 or a 1 at the output depending on what you are ANDing or ORing. This one depends on what you're comparing it to. Okay, so XORing with a 1 means that you're going to flip the bits. XORing with a 0 means that you're going to pass through whatever that value was. So again, with our mask, we used a 1, so we're going to flip the bit. Okay, this is with an XOR operator. So we're going to get 0, 0, and then here we're going to get, this one was a 0, so it becomes a 1. And there are obviously like mathematical reasons why you'd want to do this kind of mask, but this is how it would work. Okay, so if we applied the mask again, so if we did this mask with an XOR gate, and then we got this value, if we XORed it with the same mask, so if we did this and we XORed it with this, then we're going to get 1 and 0, we're going to get a 1, 1 and 0, we're going to get a 1, 1 and 1, we're going to get a 0, 0, 1, 0, 0, 0. So we're going to get back to our original value. Okay? Very simple, but it kind of shows you how you might make some kind of, cryptographic key, right? You could do that using an XOR function. All right. So if we had 5 double ampersand 6, that's the logical AND. So 6 and 5 and 6, okay? If we have 5 single ampersand 6, that's the bitwise operator, so 5 ampersand 6. Now, the bitwise is probably more obvious to you what the answer would be, whereas the logical operator, what does it mean, 5 and 6? What could that possibly mean? So let me just... All right, so here we've got, I've just set x and y to be 5 and 6. And we're just going to print the value of this. So bitwise 5 single ampersand 6, and then just for interest's sake, what 5 XOR 6 is. Okay, so let me just, no, I've already run it. So the logical, which may not be particularly logical for you all. So when you double ampersand 5 and 6, you're going to get 1. So when you do a logical AND, you're asking is it true or is it false? So 5 and 6, both numbers are bigger than 0. You've got no false in that equation, so it's going to be true. Okay? The only time that that equation is going to give you 0 is when you got a 0 as one of the inputs. Okay? Just think about your if loops or your while loops. You wait until one of those things is not true. So in sort of the equivalence is that a 0 is false and a 1 is true. Okay, so any discrete mathematicians in the audience, that's the equivalency. So a 0 is not true and a 1 is true. So when we have two numbers that are not 0, they're considered to be true. If we had a 0 number, then that's considered false. So that's why we get a 1. And you'll always just get a result that's a 1 or a 0 out of these logical operators. They're either going to be true or they're going to be false, and that's it. With the bitwise, we're doing an AND between each one of these bits. So a 1 and a 0 gives us a 0. A 0 and a 0 gives us a 0, and a 1 and 1 gives us a 1. So 4 is the answer, and that's what we would expect. And then the exclusive OR here, we've got a different number, and then the same number, and so we get 0, 0, 1, 1, which gives us a 3. Okay? So that's the difference between the operators. You'll never use these kind of logical ones really anywhere except where you're testing a condition. Okay, so for mathematicians, just to pull the joke along, any mathematicians here? Don't want to, okay. So 5 to the power of 6, that's a lot. This person would very much be dead. The software developer, as we saw, just had 3, so it's all good. So let me just... Okay. All right, so let's look at this one. All right, so this is basically just showing what I did before. So you can use your XOR as your mask or your secret key. It encrypts it into some other value, and you XOR with the same key in order to get the same thing out. Okay, so oops, I'm supposed to give a value. Oh, how many values am I supposed to give? What's happened here? Oh, okay. So oops. If I go, oops. Okay, so I put in 10 and then it XORed it with a mask. Where's my mask? Okay, that's my original value. And then when I put that value in again, it decodes it into the original value. Not particularly exciting. Probably the written words are more exciting than the actual thing. But it just explains to you how, you know, it's a pretty, I would not use this for secure things, but it gives you a little bit of a taste as to the kind of stuff that you'll do when you do cryptography, if you do cryptography. All right, so we've seen we can do AND operations, OR operations, inverter operations. Then there's the shifting operation. So a shift takes, the kind of way we'd write it is we have our binary value, and then we say how much we want to shift it. So here we have, this is our number. We say shift to the left 2 times, and these values all get shifted. So these two kind of fall out. They get taken away, and the bit positions get filled up with zeros as you shift it across. Okay, so what does this mean mathematically? Okay, so let's have a look at a few of these. If we shift 1 in 1 position, it becomes a 2. If we shift 1 2 times, it becomes a 4. If we shift it 3 times, it becomes an 8. 4 times, it becomes 16. So you can see that it's doing a multiplication, right? A multiplication or a multiplication by 2 for each bit position, or a power of 2, right? So it's a really easy way to give something to the power of 2, okay? You don't need any big circuits in order to do this very simple operation. And you know, for people that do kind of embedded systems or very power-constrained computing, using this, trying to leverage this to do multiplications saves a lot of power. All right, so let's look at shift as multiply. All right, so this, let me pull this across. All right, so this is taking an exponent, okay, and then it's, oh, here we go. It's moving 1 by the value that you put in there, okay, and then gives you the binary number. So remember on, was it Monday, we had to use these print bits files in order to avoid issues with printing binary values because it wasn't available in DCC. Okay, so we're using a power of 4, so 2 to the power of 4 is 16. And the binary number, so it started as a 1 and it's been shifted 4 places across. Okay, so this is, yeah, you can type all sorts of numbers in there and see how they move around, but the essential thing is you've got some binary numbers, you shift them and it'll give you some kind of power of 2 function. 2 to the power of function. Okay, so we can go left, so we can go right. So same sort of way we write it. So the number and then shift that number in this direction by X bit position. So here we have this number here. We shift it in two bit positions, and it will shifts this way. So this gets moved here. These two disappear off the planet, and these ones just roll around. Okay, so mathematically, what does it mean? So if we've got 1 here, we shift it one place. Well, its result is 2 to the power of 3, which is 8. So this was 16 here. And then it became an 8. Okay, and then 16 became a 4 when we shifted by 2, and then became 2 when we shifted by 3, and so on. So you can see that it's dividing by powers of 2. So the left shift multiplies, the right shift divides. Okay, so if we had this particular number here, what does this mean? When we shift, we kind of lose a bit out the end. So we've got a 7, and then the answer is 3. But if you were to put this in code, and as long as you kept things as integers, the answer would be 3, right? An integer, you can't have a fractional part. So it is correct. It's an integer. It's an integer division. So some issues with shifting. Okay, negative numbers aren't always portable, and you can't. It's not easy, depending on what system you're using, to move those around. So using shifting with negative numbers is a common issue. Always used unsigned values variables when shifting to be safe and portable. Okay, so if we look at this one. All right, so these are looking at some illegal shift operations. Okay, so we start with a -1, sorry, and we shift it to the right. Okay, and then we start with a big, probably the biggest. We're using 16 bits, so big number, and we shift it to the left. Okay, so just sort of hopefully obviously to you, if you're shifting sort of a small number to the right, weird things will start to happen. And if you shift the biggest number to the left, weird things are going to happen. Okay, and it's really just a matter of knowing, depending on how you've defined things, like this is a long unsigned, this is an unsigned 64-bit number. You can play with this code later, but you can see that depending on how things are defined, what you do, what your shift is doing, you might get unexpected things at the output. So when you're writing your code, be really sure about what you want this code to do. Okay, so let's see what we're printing at here. All right, so when we shift -1 one place, it is just, because it's all ones, it's going to keep on being a -1 as the output, and that may not have been what you wanted. This value is a big value. I think it's the second biggest or something. You shift it to the left one, and it becomes, instead of being sort of a big number, but maybe a bit smaller, you've ended up with a negative number because you've shifted beyond, you've shifted so that you've got ones in the sign bit. And then when you look at unsigned numbers, what are we printing here? So we're pushing a 1, an unsigned 64-bit 1 by 33. We get a big number. I think that sort of makes sense. And here, unsigned 32-bit number, we end up getting another big number. I suggest you play with it because I don't really want to get into the details here. This code is good for you to see unintended consequences. So how you define your, whether, a 64 unsigned versus a signed, whether, these are signed numbers, and so they do crazy things when you've got ones in the most significant bit. It becomes, you shift it, it becomes a negative bit. So all these things, unintended consequences. As I said in the other slide, do things unsigned is the best way, but also, it's how you define these particular numbers as to what you get. It might not be what you want. All right, so I really suggest you play around with that so you can see if you can get it doing what you want it to do versus weird stuff that can happen. All right, so if we are given these particular definitions here, what would the output of each of these be? So these are all unsigned, 8-bit numbers. So let's have a look. So X is going to be 0, 1, 0, 1, 0, 1, 0, 1, and Y is going to be 1, 0, 1, 0, 1, 0, 1, 0. Okay? So purposefully chosen so that they're kind of opposite land. So if you AND them, there's always a 0, so each bit is sort of lined up with a 0 in the other bit. So you're just going to get all zeros for that. Right? If you XOR, you're going to get all ones because they're all opposites. If you shift X to the left by 1, okay, so this is X. If you shift it by 1, then it's going to give you 1, 0, 1, 0, 1, 0, 1, 0, which is actually Y. Okay? If you shift Y 2 places, it's going to, I think, give you the same thing again. So 1, 0, 1, 0, 1, 0, 0, 0. Okay? If you shift to the right by 1, again, you'll get for X, you'll get a 0, 0, 1, 0, 1, 0, 1, 0. Okay, which is, part of that. Similarly for the Y value, if you do an OR between them, you're going to get all ones as well because there's always a 1 in either of the two X's or Y's. So yeah, this is just a refresh on all the things that we looked at. Hopefully it's all starting to sink in. Print get. Okay, so this this piece of code basically, if we have a big number here, we say, okay, I want to know what the fourth bit is. It'll do an AND between, it'll shift by 4 to the right, and then we'll use a mask to get out that last bit. Okay, so we put in the number n, we shift it by n, then we do an AND with 1, and then that's our result. Right, so again, not particularly exciting, but it's a good illustrator of getting your brain between integers as binary, I guess. Whoops. All right, so our number that we have here is 8, and the third bit of that is a 1. Okay, bit 2 is a 0, and all the bits otherwise are actually going to be 0. Here's a code. Okay, so we put in that number, we ask for the third bit, we put in that number, we ask for the next bit, and okay, we're printing bits. Okay, so the first two are, I guess, the interesting bits where it tells you which bit is there. That's using both masking and so shifting and then masking. Presumably, and it should be obvious that it's fairly straightforward to actually create a mask. But this way of doing it means that you don't have to create individual masks for whatever value of n is. So you shift it n places and then you use the same mask rather than creating a new mask every time you get your value of n, if that makes sense. All right. So again, another piece of code to play around with. Okay, so in MIPS, you've got all sorts of bit manipulation instructions, and, or, XOR, NOR, ANDing with a constant value, ORing with a constant, XORing constant. There's the NOT value. There's also lots of shifts in there. So shift right. This one and this one. These ones will shift zeros into the most significant bit, so they'll sort of assume that they're unsigned. Sorry, shift left. Sorry, will shift zeros, and then shift right will propagate the most significant bit. So these ones, your sign is maintained, and these ones are, you know, matching the unsigned shift that you use in C. All right, so let's. All right, so odd even. All right, so we have this. See, last time we said there's no more MIPS, but there's a little bit more MIPS. All right, so we have this code here, which we have the value 5. Then we find the remainder after we divide it by 2. If that is equal to 0, then we're going to branch to here and say it's an even number. And if it's not 0, then we're going to say that it's odd. Okay, so let's just see what that looks like. Oh, do I have to get? That's what it had. Why isn't it working? I'm not really sure why that's not working. If anyone sees where the problem is, let me know. Ah, okay. Sorry, it's not loading 5. It's waiting for me to give it a number. All right, silly me. All right, so 7 odd, 8 even. Okay, it works. As we said before, that's how you do the code. How would you do this, or how could we modify it in order to use bits? So if we remember from before, all odd binary numbers have 1 in the least significant bit. So perhaps if we did something like AND with 1, okay? So the number that we type in, if we AND it with a 1, which is all zeros and then least significant bit 1, then if that is 0, then we know that it's a even number, and if it's 1, then we know that it's an odd number. Okay, so here we're doing n ANDed with 1. Okay, so all right, so not very surprisingly, it works as before. So we just, instead of doing a modulus operation, we now do an AND. And actually in the hardware, doing an AND is orders of magnitude cheaper than doing a division with a remainder. So even though in lines of code it's the same, this is like one gate that uses minuscule amounts of power, and doing a modulus would use significantly, probably orders of magnitude more. So important as programmers to understand some of your choices can actually mean big differences in the amount of power and compute that's required. An AND gate is always going to be cheaper than any kind of arithmetic operation. Okay, so here we have an unsigned bit 42. We're going to do a shift, and then we're going to print out what that is. So I said that there was a bunch of different shift operators, so we want to shift to the right. And depending on which one we use, we're going to either have a signed or an unsigned situation. So let's have a look. All right, let me just, this has not been very smooth. All right, so we'll just have a look here at what sort of options we have. Okay, so we've got a logical shift, okay, an arithmetic variable shift, and an arithmetic shift. So from the previous slides, we saw that the arithmetic shift was going to be a signed shift, and this will be just a logical shift. So let's try them out and see what we get in the two places. All right, so we go shift right logical, what was it? So T0, and how many places? We want to do one place, and we want to do it unsigned. Okay, and then we're going to do shift it to the left. Okay, and we're going to print it out. Oops, MIPS. MIPS. Oops, no. Okay, so you can, as an exercise, work out whether it's done the right thing. Kind of running out of time, and I don't want to get booted out by the next person, so let's just quickly wrap it up. All right. Okay. Oh wow, great timing. So we looked at integers again. We looked at bitwise operators. Next week, we'll start looking at floating point. We'll go through a few more bitwise examples just to boot your brain back into it. Feedback always welcome. Forum, reach out if you need help. If you need other help, please seek it out before it gets too big. Thank you for coming on this very cold morning. Have a lovely day, and I'll see you next week. Don't forget, you've got your test due and your assignment and all of that stuff. Good luck.